Right, welcome to part 2 of 2 on earthquakes and hazards. So in part 1, we had just finished talking about deformation and how the rocks were actually breaking. And now we're going to think about the flip side of that, which is these seismic waves that are induced. So when brittle failure occurs and we eventually release that earthquake, there is some energy, and the energy has to go somewhere, right? So this GIF on the left here is an imperfect example of this. So when that rubber band or slingshot snaps, it just falls to the ground. But we know that's not really how it occurs. If you take a rubber band and you snap it, it continues to reverberate through time, right? And that's the energy that's being released. You can't just release it and have the energy completely go away. Instead, it's got to dissipate in some form. And so this video on the right, which the link is broken, but that would basically just show that as you hit that rubber band, we have that, that vibration response and that energy released. That energy released in earthquakes is going to be what really causes the hazard. So one part of that energy release is going to go towards frictional heating. So when you release that rubber band, if you get really close to it, the rubber band has warmed up some, and that's frictional heating. That frictional heating in terms of earthquakes is going to impact the rocks near it. And so that can kind of fuse some rocks in these really neat formations. So this is a type of rock called fault gouge. And it's the broken up rock that is formed around earthquakes, often broken up because of that rock fracturing, the mechanics of that. And then it's heated by that energy release and kind of fused together. So these are some images showing fault gouge. There's a strain of it right here, and then kind of like a much more messier bit of fault gouge on the right picture. But what we're really concerned about in this lecture while we think about earthquakes is the oscillatory motion. So this is the seismic waves. So as the earthquake breaks or the focus, these waves are going to travel out away from the focus or the hypocenter of the earthquake, and they're going to start to interact with the ground surface, and they're also going to travel a lot further than that original rock breaking. So the first half of the earthquakes where the rocks are actually breaking, that might be occurring just here in this red line around the hypocenter or the focus, and that's not really impacting directly any of us in terms of hazards. However, these seismic waves are going to travel not just to the immediate surface, but they're going to travel around the world. And there are 3 types of seismic waves. Each of these has different hazards associated with it, and each of them also have different travel speeds. So we'll start off with the surface waves. So these are also called Rayleigh waves, and they're responsible for most of the damage that we see from earthquakes. In this GIF, you can see an example of how these travel. You can see why they're named surface waves. They are kind of mostly traveling closer to the surface in a circular motion, and that motion decreases as we get further down in depth. This is kind of similar to how ocean waves also travel. These are responsible for most of the damage because they are on the surface, and that's also where we are. And they tend to be amplified by rock type. So types of rocks like granites, which is a crystalline hard rock, because they are locked in place, all of the crystals are locked next to another crystal. They tend to not propagate motion as well as softer rocks do, like sediments. So a sandstone or just sediments that aren't even a rock yet are going to propagate these surface waves really rapidly because there is that space for the particles to move independent of each other. This is slightly unfortunate because many of our cities were built near rivers and near ports, and ports tend to have a lot of soft sediment. So hazards from surface waves are a big topic of conversation in places like Seattle and San Francisco, where they pose a really large risk to infrastructure and to people because most of those cities are built on soft sediments. Kind Kind of moving to the next type of waves are P waves. These are called primary waves, as abbreviated as P waves. These can move through both solids and liquids, so they can move through water as well as through the hard rock at speeds of about 5.5 kilometers per second in granite and 1.5 kilometers per second in water. That's really fast. And the way they move is in this push motion. So the particles are moving forward and backward to create waves that propagate through basically compression of particles and then expansion of particles. So if you've played with slinkies, this would be an example where if you have two people who stretch out the slinky, you just push the slinky at them like that. So there's no up and down motion. You're just pushing it directly at them. And you're going to recreate a primary wave by doing that. The last type of wave are S waves or love waves. These you can also make with your slinky. So if you hold your slinky up with your friend, instead of pushing, just kind of oscillate it up and down, and that's an S wave. So these are shear or secondary waves. And they move through this lateral motion. So you can see that in this GIF really nicely. If you just focus on the top part, you can see those particles moving back and forth relative to each other. Because they really rely on this back and forth movement, they cannot move through liquid. So you cannot actually recreate this type of wave in a liquid. It's just going to dissipate out. And they travel a lot slower through hard rock as well. At speeds of about 3 kilometers per second in granite, and of course 0 kilometers per second in water. This unique property of S waves is going to be really important because we can identify areas that are liquid if P waves travel through them, but S waves don't. But the main reason I wanted to talk about these, aside from hazards, are that they help us identify where the earthquake is coming from. So the earthquake waves will arrive, usually P wave first, then the S wave, and then the surface waves, just based on their different speeds. And because they have different speeds, we can use that to figure out how far away the earthquake is from a seismometer. So in this seismograph here, you can see an example of when an earthquake hits. So you have this background noise, and then you have the initial disturbance. That's the P wave, the primary wave. That disturbance continues, and then it's amplified suddenly when the first S wave hits. And right on the edge of that S wave are going to be the rest of the surface waves. So we can use the time. Sorry, accidentally left the PowerPoint for a sec. So we can use the time between the P and the S waves to say how long it's been, right? So we could say this has been 1 second between them. And if we know that this was traveling at 8 kilometers per second and 3 kilometers per second, we can use those rates and that time to figure out an actual distance. And this is a really nice example of how we do that. Here is one earthquake and how it's been recorded on 14 different seismic stations. And these seismic stations are ordered by their distance away from the earthquake. And you can see on each of these that the different arrival times. So we have first the P waves arriving, and then the S waves. And that distance between the P and the S wave arrival is increasing with increasing distance away from the earthquake. So we can use that time between P and S wave arrival to calculate what the distance is. And if we have a seismic station, we can then draw a radius with that distance around the seismic station and say, well, the earthquake must have occurred somewhere along this line, this radius. Unfortunately, we don't have enough information to pinpoint where it actually is. But if we can get 2 other seismic stations, we can do what's called triangulation. So the second seismic station, we measure the time between P and S wave arrival, get distance out of that, and then draw a radius. But now we have 2 potential points. So there were 2 areas where that first seismic station and the second one intercepted. So that's where the third one comes in handy. And when we draw that line through, there's only one location where all 3 intersect, and that is the earthquake location. Okay, so these seismic waves are going to be emitted from earthquakes. They're going to be responsible for some of the hazards, particularly surface waves, but we need some way to actually define what the earthquake strength and hazard is. Otherwise, we're kind of comparing apples and oranges with every single earthquake. So there's two main schemes that we do this by, magnitude and intensity. And both of these are different ways to define what an earthquake strength is and compare between earthquakes. The magnitude is what you're probably most used to. It's a numeric scale of how much energy is released. And there are two different types of magnitude scales. So the first one is the Richter scale, which is often just symbolized by an M. And this was really commonly used for a long time and is still, I think colloquially, we think of the Richter scale as being the magnitude. This is actually not the one that we commonly use today. So I'll just keep that in mind. But the Richter scale would measure the largest seismic wave on a seismometer that was recorded 100 kilometers away. So in this example view in the center here, here's the seismogram from 100 kilometers away from an earthquake, and the largest wave got this high. The amplitude of that wave, or how high it is from the background level, is measured. It's 10 centimeters. And so that 10 centimeters, which is 100,000 microns, was used to figure out the Richter scale. We took the log of that and found that the log was 5. Just a note, the log of 100,000 is basically saying what power is 10 raised to get to 100,000, and 10 is raised to a power of 5 to get to 100,000. Okay, so that was how we got the Richter scale. It's important to note that it's logarithmic. So an increase from a Richter scale magnitude of 5 to 6 is a difference in measurement of 100,000 microns and 1 million microns. In terms of energy, that's equivalent to 32 times greater energy release. The Richter scale will go up to 10. It can't go any higher than that. And what we've seen is the amount of earthquakes tend to decrease with increasing magnitude. So this diagram on the far right is showing that we've got the Richter magnitude, some major events on the far right, and then the maximum ground motion measured on the seismogram. So that's just another way to say what the Richter magnitude is. And then this scale here is kind of showing us, how the numbers of them are branching off as we get to be higher and higher magnitudes. So examples of this, the 2020 Salt Lake City earthquake fairly recently was a magnitude 5.7. The 1989 earthquake in Bay Area was 6.9. One of the largest earthquakes in the United States was the 9.2 1964 Alaska earthquake. Okay, so the Richter scale was used for a while, but it was so dependent on the distance from an earthquake, and that energy release is going to, the size of this point on the seismogram 100 kilometers away is also going to depend on what's in between the earthquake and that 100 kilometers. And so to try and relate the earthquake strength directly to the earthquake itself, we now start to use the moment magnitude, or M sub W scale. So this is what's commonly used today. If you're looking at the USGS, you will see moment magnitude used. So it's not dependent on distance, but actually on direct earthquake information. However, a lot of this information isn't readily available right away, and so you may see these magnitudes adjust over a period of days as we get new information. That's just what I wanted to note at the bottom there. This measurement is a combination of strain, so how much offset actually occurred the earthquake, the area of the fault that actually slipped, and then the strength of the rock that was involved in the slipping. So these are all key constraints that go into energy release. And so here we're actually measuring more directly the energy released rather than relying on a proxy measurement, which is what the Richter scale did. The two are fairly related though. We can see here a comparison of the Richter magnitudes on the x-axis and the moment magnitudes on the y-axis. And these follow fairly well a one-to-one scale. There are some instances where the Richter magnitude overestimates the energy and some instances where it underestimates. But overall, they're fairly close. Just to give an idea of how much energy is released, here we'll look at the number of earthquakes, the magnitude of the earthquake, some examples of earthquakes, and then the energy equivalent in terms of events, and then in terms of kilograms of explosive. So these are all somewhat older earthquakes, so we may only know of them through memory. But you can see the average tornado is coming in at a less than 5 magnitude scale. The Hiroshima atomic bomb is a little bit greater than 6 moment magnitude. Mount St. Helens is a little bit less than 8 moment magnitude. And the major earthquakes in the world, the Chile in 1960 and Alaska 1964 earthquakes, that were both above a magnitude 9, it's not really an energy equivalent event, and they're releasing somewhere in the trillions of kilograms of explosive. All right, so we're going to commonly use moment magnitude when we talk about earthquakes, but if you go on the USGS site, you'll also see something called the earthquake intensity. And this is a scale that's really keyed to what humans are experiencing. So it's a very subjective scale, which means it's going to vary depending where you are in distance from the earthquake. And it's also really going to depend on what the reporter's intuition is. How intense did you think it is? And that may vary person by person. So this is also called the Mercalli scale, and it's going to use Roman numerals ranging from 1 to 12, where 1 is not felt except by a few people, and 12 is just completely total damage. You can see the earth actually forming waves on the ground surface. Your line of sight is distorted and objects are thrown in the air. Because these relate to the damage, and damage is going to be somewhat dependent on the distance away from the original earthquake. This means that the Mercalli scale is going to differ depending where you are. So there's going to be multiple Mercalli scale intensity ratings for a single earthquake, whereas there will only be one magnitude rating for a single earthquake. So for almost any earthquake, you can go to the USGS site and you will see a map that looks like this. And this just shows spatially what the Mercalli scale was for that earthquake. So this is the 2001 Nisqually earthquake. This was the first major earthquake that I felt. And you can see that, it originated, its epicenter was a little bit north of the city of Olympia near Nisqually. And as he traveled away from it, the Mercalli scale tended to decrease. But there are areas where there was some increase, and a lot of that has to do with what the ground surface is. So you're getting into areas here where there's a lot of soft sediment, and that's going to amplify the surface waves and make the intensity of the earthquake even greater. The same thing kind of in this area. This is another soft sediment area. That's actually where I was. It's right there. Okay, so when you talk to people about earthquakes, especially as a geologist or a seismologist, you're going to get asked the question, can we predict earthquakes? And if you get anything out of this one lecture, no, we cannot predict earthquakes. Never say yes, always say no. And the clarification for this is we cannot predict when an earthquake event will occur, but we are getting pretty good at assessing whether or not there is a risk of an earthquake occurring. And this is where we're at. We're never going to be able to say yes or no, an earthquake is occurring tomorrow. That's just, there's no way we can understand the earth that well. but we can say what is the percent likelihood of an earthquake occurring in the next 50 years of this magnitude. And we can do this through looking at evidence of past earthquakes. So we've gotten very good at assessing what the past earthquake history has been, which helps us inform what the future earthquake risk will be. Much in the same way that when we talked about flooding, we looked at the history of river floods and looked at how frequently they occurred. And that gave us these percentage exceedance, which was basically assessing what the flood risk was in the future. So one way that in terms of earthquakes, we can look for evidence of this. We can trench across faults and look for signs of prior earthquakes, and we can try and date those earthquakes. Okay, so this is an example of what the fault trench might look like originally. You can see there's some layers of fine sand. There's some gravels. And if you look closely, you can see small breaks in those. And so that's the interpretation that's on the bottom here, is all of those breaks in places where we see small offset-like faults. And then whenever we see that offset, we can try and find some datable material to figure out when that offset occurred. Okay. And when we do this, we can compile a list of, for earthquakes we've trenched, we can see whether or not they've been active in the last 10,000 years. And so we classify faults through this general rating, where faults that are classified as active and therefore posing an earthquake risk are faults that have had movement during the last 10,000 years or during the last during the Holocene. Potentially active faults are those that have had a movement in the Quaternary in the last 2 million years. And we can't rule out that because they haven't been active in the last 10,000 years, they may not be active in the future. And then faults that are inactive are ones in which we have not seen any movement in the last 2 million years. And so through this method, we can get these short-term seismic hazard maps. So here's one from the US Geological Survey for the conterminous United States. And you can see what the chance is of potential minor damage from ground shaking in the year 2018, where white is no chance. So you can see we're over here, we're in this zone. We don't really expect to get much damage from ground shaking, at least back in 2018. And then it's going to increase in the dark, rather, the 10% to 14% chance of minor ground shaking. So there's some interesting patterns here. We see hotspots near Seattle, through California, in Oklahoma, and then kind of in this junction of Tennessee, Kentucky, Missouri. So take a second and think about, why is there elevated seismic risk in each of these areas? All right. So if you think you've got some answers, let's proceed. We'll start out with California. So here along this zone of red is the San Andreas Fault, which is a transform plate boundary and a strike slip fault that is highly active. There are also a lot of areas, such as the Bay Area that was in dark red there, that is made of unconsolidated sediments, which are very prone to shaking by surface waves. And so these two combined, having an active plate boundary with a long history, an active history of earthquakes, and combining that with the ground surface, gives us the greater chance of minor damage from ground shaking. In the Seattle area, we have some surface faults in the Seattle area, as well as the Cascadia subduction zone offshore. That's going to increase the hazard here. In Oklahoma, mostly what we're looking at there is probably earthquakes from fracking. This would be extraction of natural gas through pumping of waters and other liquids, and kind of artificially creating earthquakes that are fracturing up the ground. And so that's most likely what we're seeing in Oklahoma. And in this last spot, there actually is some tectonic activity in the middle of of the United States that's going on, it's fairly inactive. So you can see the percent here is 2 to 5% of minor ground damage. So it's not very active, but there are some tectonic structures in the middle of the US. All right, so that's kind of the end of earthquakes and earthquake hazards for us. And what I'd like you to do now is to revisit the risk assessment that you made at the beginning of class. And we're going to supplement this now with some data. So the USGS has compiled a nice web map that has faults on it and some activity along those faults. And so what I'd like you to do is to take those 3 to 5 places you came up with at the beginning and your hypothesis about which place had the greatest earthquake risk and compare it to this map. And then I'd like you to turn in a revised earthquake risk statement that compares those 3 to 5 locations that you came up with this and references back to this fault map to identify which ones do have the greatest earthquake risk. And I will put the link to this fault map on Canvas, so you will be able to find it next to the link to this lecture.